everyone. I'm Eric Williams with Vector Corrosion Technologies, and I want to welcome everybody to the Webinar Wednesday series, proudly hosted by the Concrete Preservation Alliance. Over the course of these series, we'll be diving into advanced assessments, and what we're going to be doing with that is exploring real-world investigative techniques for post-tension voids, corrosion, condition assessments, post-disaster testing, and unknown foundations. So if you are in the world of structural repair or asset management, I think you're going to really get a lot out of this series and enjoy it. So today's session is titled What Remains? Condition Assessments After Extreme Weather Events. In this session, we'll be sharing how both non-destructive and destructive testing methods are used to evaluate damage in concrete structures after events like fires and floods. These techniques help us detect hidden issues, guide repair decisions, and ultimately play a critical role in restoring and strengthening infrastructure after disaster strikes. If you're new to the Concrete Preservation Alliance, welcome. We're a coalition dedicated to promoting best practices in concrete repair and preservation. Our mission is to offer free, accessible, and non-commercialized education, sharing practical knowledge from professionals in the field to support long-term durability and sustainable infrastructure. We extend our sincerest thanks to all of our members and supporters who have been supporting these events for several years now that we've been doing them, and the collaboration and dedication that make the Concrete Preservation Alliance in the educational events like this possible. We very, very much appreciate it. So if you had former sessions, you can catch replays of these past sessions, plus you can download presentation slides on our website here, wesavestructures.info. And then while you're there, we also do have an environmental impact calculator. That is a free tool that helps you estimate the environmental benefits of repairing versus replacing concrete structures. So the first one up is Natalia Shanahan. Natalia is a senior project engineer or senior project manager and a professional engineer at VCS Engineering. She has 15 years of experience and has been with VCS for over 7 years. Bill Horn, he is the vice president at NDT division of VCS Engineering. He is also a professional engineer and with over 30 years of experience in the bridge market, and has been with NDT and VCS Engineering for the past 8 years. So thank you to both of you for being here today and going to sharing some of this knowledge. And I think Natalia is going to be the first one to take it away. So I'll throw it over to her and appreciate everyone being here. Thank you.
Thank you, Eric. So in today's presentation, we're mainly going to focus on two types of extreme weather events, fires and flooding. We're going to discuss various non-destructive testing techniques that we typically use to assess the effects of these weather events on existing structures. And then Bill and I are also going to present some case studies. When a reinforced concrete structure is exposed to fire, the effect on concrete is that at first concrete starts to crack. As the exposure continues, concrete will begin to spall, and as the temperature of the concrete increases, it's going to begin to lose its strength and elastic modulus. Concrete is not a very good conductor of heat. However, if it's not a short fire, eventually the high temperatures are going to reach the rebar as well. When that happens, the steel is going to start losing its mechanical properties. The evaluation techniques that we typically use for fire-affected structures are impact echo pulse velocity testing, which I'm going to talk about in detail shortly, collection of concrete cores for compressive strength testing, and collection of rebar samples for steel testing. With floods, there are several concerns. First, floodwaters carry with them a lot of moisture that can get into the concrete and cause reinforcement corrosion. If the flooding occurs in coastal areas, floodwaters also carry aggressive ions with them, such as chlorides, that can also diffuse from the surface into the concrete to the rebar depth and initiate corrosion. Floodwaters sometimes can dislodge large objects that impact structures and cause cracking and spalling. In addition to damage to reinforced concrete, floods also cause soil washout as well as scour, and this can undermine the integrity of the structure. The evaluation techniques that we use in case of flooding are corrosion potential surveys and chloride sampling for reinforced concrete, impact echo and pulse velocity testing for crack depth measurements. We use GPR to locate voids and moisture infiltration in the soil. Impact echo pulse velocity testing for determining cracking in piles and pile lengths determination, as well as seismic refraction for identifying scour. Both impact echo and pulse velocity tests use acoustic waves. In the case of the impact echo testing, we are measuring the frequency of the generated waves, which can be related to the thickness of the concrete element. And in the case of pulse velocity, as the name suggests, we're measuring the wave velocity through the concrete. Next, please. The equipment that we use has an impact device that is powered by compressed gas that shoots a BB at the concrete surface. The BB impact generates a wave in the concrete, and the propagation of the wave is monitored by a force sensor array. The array that we have is 2.5 feet long and has sensors at a known spacing. The signal picked up by the array is recorded by the computer. This equipment collects both impact echo and pulse velocity data at the same time. When we are looking at the impact echo data, we're typically looking at sensors 1 and 2, although all 4 sensors collect both impact echo and pulse velocity data. For pulse velocity, most often we're looking at sensors 3 and 4. However, when we're interested in the very near surface condition of the concrete, we are looking at sensor 2 as well. This video illustrates how acoustic wave travels through the concrete and the effect of a defect on the travel path of the wave. The defect in this video is indicated by a horizontal white line. And in a real structure, this can be a crack, a delamination, or a void in the concrete. So as you can see in the video, the wave travels around the defect, so the defect can be easily identified. In an area that is free of defects, the wave is reflected from the back surface of the concrete element. Next, please. The pulse velocity data is collected per ASTM C597. Here, as I mentioned previously, we're measuring the velocity of the wave. What we're actually recording is the time of the wave arrival at each sensor. We have the time, we have the distance between the sensors, we can calculate the velocity. In the sound competent concrete, the wave velocity is expected to be equal to the typical concrete wave velocity. However, when we have cracking in the concrete, the energy of the wave is going to be dissipated by the cracks. So what we're going to measure is a decrease in the wave velocity that indicates the presence of cracking. In addition to that, cracks are also going to change the shape of the waveform, which we're going to see on the next slide. And when we have a delamination, we're going to have a significant reduction in velocity, as well as a significant impact on the shape of the waveform. So the pulse velocity data, in addition to identifying areas of cracking and delaminations, can be used to estimate the in-place compressive strength of the concrete, because velocity of the wave is related to the Poisson's ratio and elastic modulus. The impact echo data is collected per ASTM C 1383. Here, the wave travels from the concrete surface and is reflected back from the back face of the element. With the presence of cracking, cracks absorb all of the energy of the wave, and we will not get a response compared to the sound concrete that's going to give us the actual thickness of the element. In case of delaminations, very similar to the pulse velocity, we're going to have a very distorted waveform. Next slide, please. So here, the left side of the slide shows typical pulse velocity data that is collected on sound concrete. These are the waveforms that you're seeing on the top of the figure. From cracked concrete, that's waveforms highlighted in yellow, and then in delaminated areas, which are highlighted in red. As you can see here, delaminations and cracked areas are distinctly different from sound concrete, and we can easily identify them during the testing. The plot on the right side of the graph shows the relationship between the wave velocity and the dynamic compressive strength. We can also use this test method to estimate the depth of cracks. So this can be used in flooding or in other applications. The principle here is shown on the left side of the slide. As you can see, we can relate the distance between the crack and the transmitter and receiver to the depth of the crack. And then the right side of the slide shows the schematic of how the testing is typically done. We start by placing the transmitter and receiver really close to the crack, and then we move them further and further away. If the distance between the crack and the transmitter and receiver is too short, it will not allow the wave to travel across the crack, so we won't get a signal from the receiver to the transmitter. As we move the transmitter and receiver away from the crack, we're looking for the distance where we can first detect the wave arrival at the receiver. And based on that distance, we can then estimate the depth of the crack. Another application of IAPV testing is through tomography. This is typically used when we need to assess the internal condition of an element beyond just collecting measurements from the surface, which is what is typically done with the IAPV array setup. So here, instead of placing the impactor and the array right next to each other, we place the impactor on one side of the element and the array on the opposite side. We then move the array and the impact device to create these multiple intersecting paths through the element that you can see on the right side. These multiple intersecting paths allow us to create a 3D image of the element. We have a special software that can process this data and then essentially slice through the element, giving us the condition or a 2D representation of the condition of the element at various depths. Next slide, please. This is an example of through tomography testing. So here we tested a closure pore between two large precast concrete column elements, and that's the photo that you see on the left side of the slide. For this particular project, there was a concern with consolidation for the closure pore. So we did through tomography testing, collecting data on both sides with multiple paths. We put it into the software and then stepped through in slices through the entire element thickness. The color plot that you see on the right side of the slide represents a thickness from the middle of the, represents a slice from the middle of the element thickness. And a void was identified at this location. And the void here is indicated by the light blue and green colors in the middle. IEPV testing can also be used for pile length determination. So after storms, sometimes either vehicles or boats are dislodged, and they can impact bridge piles or building piles and cause cracking. This cracking is not always visible above the water. So this test method allows us to determine whether or not the piles are cracked and estimate the depth to the cracking. The principle here is the pile is impacted near the top. The impact generates an impact echo wave that travels along the length of the pile and is reflected from the tip. We're measuring the time that it takes the wave to arrive back to the sensor. If we know the time, we know the velocity, we can calculate the length of the pile. Where we have significant cracking, instead of reflecting from the tip of the pile, the wave will be reflected from the crack. And this is how we can determine the depth to the crack location. Another versatile condition evaluation technique that we use quite often is ground penetrating radar. GPR is a non-destructive electromagnetic testing method that sends electromagnetic waves into the media that you're testing. So typically that's concrete or soil. The GPR signal is then reflected back from interfaces with different dielectric constants. So in reinforced concrete, that would be the interface between concrete and rebar, or concrete and large voids, for example, voids and hollow core slabs. GPR is not very good at locating small voids like consolidation voids. In the soil, the reflections come from air-water interfaces or air-void interfaces, as well as interfaces between different soil types with very large differences in dielectric constant, for example, rock and sand. GPR units come in a variety of frequencies that range from 100 megahertz to 2700 megahertz. Low frequency antennas are typically used for looking at soils. They have a very good depth of penetration, but they have poor near surface resolution. So when we need really good near surface resolution, for example, when we're looking at reinforced concrete, we want to use high frequency GPR. Now, the downside of that is that high frequency GPR has a poor depth of penetration. So typically it's limited to 1 to 2 feet. Next slide, please. We use high frequency GPR to determine the reinforcement layout. What you're seeing here are the typical GPR scans collected on reinforced concrete elements, and the bright white peaks that you're seeing are the rebar. We can also use GPR to determine the element thickness. That's the black horizontal line that you see in the scans. For evaluation of flood-affected structures, we're using GPR to determine the reinforcement depth, because in the case of flooding, we're concerned with exposure to aggressive ions, such as chlorides, and we need to know the actual cover depth of the reinforcement, so we can look at the progression of chloride concentration between the surface and the rebar depth. Next slide, please. This slide shows examples of different GPR scans that were collected with a low frequency antenna. The scan on the left shows soil with bedrock, and that's what you see sketched out below the scan. And on the right side in the top is an example of a void in the soil, and below it is a reflection from a buried pipe. When we're concerned about corrosion, the best test method to locate areas of active corrosion is the corrosion potential survey, also known as half self-testing. This test is performed per ASTM C876. Here, an electrical connection is made to the rebar, and the rebar is connected to the positive terminal of the voltmeter. The negative terminal is connected to a reference electrode that is placed on a grid along the surface of the concrete element. And the potential at each tested location is recorded. ASTM gives us guidance on how to interpret these potential values. ASTM says that anything that is more positive than negative 200 millivolts is at 90% probability of being passive. Anything that is more negative than negative 350 is at 90% probability of active corrosion. And in between, corrosion is in an uncertain range. This slide illustrates the corrosion potential testing. So step number 1 is to locate the rebar with GPR. Step number 2, drill to the rebar and make an electrical connection. And step number 3 is to place the reference electrode on the surface of the concrete and record the potential measurements. And now I'm going to pass it over to Bill to talk about seismic refraction and scour.
Great, thank you, Natalia. You can hear me okay, correct?
Yes.
Wonderful. So seismic refraction is more of a typical geophysical test method. We cover much larger areas. Our sensors are geophones or hydrophones if we're in a marine environment, and our energy source is a lot more powerful than an air gun that was shown before. So typically the energy sources are from a size gun, which is a black powder 10 gauge shotgun shell. It is embedded into the ground with a small little safe blasting mat and a firing pin hit by a hammer. The geophones or hydrophones are spaced 5 or 10 feet apart over an array of 100 feet long, maybe 200, even 400 foot long. We're still recording the velocity of the energy waves, and where the velocities are higher, the strength of the rock or the soil is greater. Where there's low velocities, that is where the weaker soil or rocks exist. This is an ASTM procedure. It's in the D side of things, which is the geotechnical 5777. The refraction equipment is portable. On the left is the hydrophone array that is getting stretched out in a riverbed. This is for a scour investigation to determine, is the abutment or pier completely founded on rock? And then the energy source is in the middle. There you can see the size gun and the hammer, just as a demonstration. In the upper right is all of the equipment. It's powered by a battery, so very portable. And the cables are in the foreground there. The lower right image is a geophone that is stuck with a small spike into the ground. It's basically a magnet that is suspended on a spring and connected to the electrical cord to determine the time differential from when the energy impact takes place. An example of where this is good is in a river environment. This happened to be about knee-deep water. Wouldn't be able to really float a barge, and driving a track-mounted drill rig to get subsurface information would be very challenging. But in a short period of time, we were able to get a continuous line of data on where the bedrock was, the depth and the strength of the bedrock from the shear wave velocity. There's other ways to get strengths for RQD. If we're collecting pieces of the rock from a core, we can measure the number of pieces and equate that to the strength. If there's a big enough piece of rock in the core barrel, we can trim that and break it, or we can get the shear wave velocity. Caterpillar to this day uses shear wave velocities to quantify the strength of rock. That 3-to-1 ratio is very important. We need to have 3 times the distance on the surface to the depth that we're investigating. So if we want to get information 100 feet in the ground, we have to have at least 300 feet of hydrophones or geophones collecting data. This is the example of this alignment that I showed you in the previous slide. We collected 1,400 lineal feet continuous profile data of the rock for the proposed alignment, which is the hypotenuse, and determined the rock was about 14, 15 feet down. It was a weathered shale that was competent enough to support a spread footing. So done early on, it was able to reduce the number of borings. It doesn't eliminate the borings because it doesn't give you the detailed information you need for bearing capacities. So split spoon sampling or cone penetrometer is still needed for bearing capacities, but it does reduce the number of them, gives you a continuous profile. It's very efficient and cost effective, especially done prior to a typical subsurface investigation. Now, in talking about scour, which was the introduction for this seismic refraction testing, scour is the #1 cause of bridge failures in the world. And with some of the events that we've had recently, West Virginia, down in North Carolina, the coastal events, we seem to get larger storms with more precipitation more frequently. So when all this water is in a river, it is coming down and it hits an obstruction like a pier, and that water is forced around the pier. It creates what's called a horseshoe vortex. It speeds up, and that velocity increase going around the obstruction can remove the soil from the support, the abutment or the pier. And that causes instability. If it's a spread footing, it could undermine the footing. And if it's a pile supported structure, it could weaken that because you wouldn't have the bracing of the soil to support the pile. So local scour is a concern. And it can be additive with contraction scour if you're contracting or squeezing the river flow between 2 abutments. In hydraulics, the flow equals the area times the velocity. And if the area is fixed, like between 2 abutments, and the flow is coming through, it gets squeezed in there or contracted, the velocity is going to speed up. So that could also increase the erosion of the soil. So where there is a pier obstruction and a contraction in a floodplain, you can have 2 types of scour that are additive. Again, when there is flooding, we recognize that the precipitation events, thunderstorms, 2 inches an hour or even more, can increase the flow in rivers. On the right is a picture of the obstruction, hydraulic turbulence that's caused by that pier on this 2-span arch. So that water is squeezed in between these 2 barrels and the velocity is increasing. That's going to erode the soil and could threaten the integrity of the bridge. And then, as Natalia mentioned, debris also contributes things. Tires, trees, what have you. In the Northeast in winter, during some of the springtime ice breakups, ice forces can be very dramatic and also impact the flow area. The water's not going to stop. It's just going to speed up. And if there's an ice jam, it may disturb that ice and dislodge it until it floats downstream and impacts against another bridge. Again, bridge scour is the #1 cause of bridge failures all over the world. And it was very evident in 1987. There was a bridge failure on the New York State Thruway just outside of Albany, New York. The Schoharie Creek overflowed. On the left image, the channel is on the left side of that image where the bridge has failed. But the floodplain is all the way across that image. So all the water was forced back into the channel, sped up, and eroded the soil on Piers 2 and Pier 3, and that was a spread footing. There developed a crack in that, and ultimately it failed, and the bridge collapsed. A very tragic failure. There was other bridge failures that prompted the Federal Highway Administration to come up with guidelines on predicting scour for existing structures as well as new structures. And it's not just vehicular bridges. Railroad bridges are also susceptible. In fact, Railroad bridges may be more susceptible because they often travel along rivers to minimize the steep grades of going up and down, but they are susceptible as well. But if you see some water on the road and a local bridge or a big bridge, turn around, don't drown. That's a very valid warning, and you never know if the bridge or the abutment or the road has been compromised, and the flow forces from the water can carry cars right away. We see that in flood events all the time. So as a summary, the bridge inspection standards, there's all sorts of items to rate bridges. One is 113, which is scour vulnerability. The impact echo pulse velocity can be used to determine the embedment. That means the spread footing embedment or the pile length and the changes of those, or if the piles have been compromised, the debris could impact timber piles and threaten them. Refraction survey, as a proactive measure, can determine where the elevation is of the rock, and if the abutments are founded on rock, they are probably less vulnerable. The hydraulic modeling quantifies the floods with velocity and elevation of the water. HEC 18, hydraulic engineering circular 18 and 20 quantify what the riverbed particle size is for calculating those scour depths. And if a bridge is rated scour critical, there needs to be a plan of action. Maybe there's some countermeasures, revetment that needs to be designed and placed, or maybe the bridge is so vulnerable it just needs to be closed during a particular flood event. Now we're going to get into some case studies, and we're going to have Natalia start us off with some fire damage of bridge abutments and other structures, and then I'll finish up with some freeze-thaw case studies.
Thank you, Bill. Our first fire damage project is an I-95 fire in Connecticut. This was a very large fire that made the news. Here, a tanker got stuck under the bridge and caught fire, and the fire burned for quite a while. And as you can see in these photos, it caused a lot of damage. The bridge deck had collapsed, and so did the superstructure. So what was left remaining was the abutment and pier. Connecticut DOT wanted to see if the abutment could be potentially salvaged. So they contacted us to do some testing on the abutment. Our testing consisted of collecting samples as well as impact echo pulse velocity testing. So what you see on this slide from left to right is GPR scanning to locate rebar. In the middle, we're collecting cores, concrete cores for compressive strength testing per ASTM C42. And then on the right side, we are extracting a piece of rebar for testing as well. And this slide shows impact echo pulse velocity testing. We did testing on a grid throughout the entire abutment. So we could generate what we call heat maps, which are essentially color plots of the condition of the abutment. Next, please. Okay. What you're seeing here on the right side of the slide is data from our 3 different sensors, sensor 2, 3, and 4. If you remember the image of the sensor array, sensor 2 was the closest to the impact device. So it represents the near surface condition of the concrete. So sensor 2 has a penetration of about 2 inches from the concrete surface. As can be expected, the condition of the concrete surface was very poor, as indicated by the dark red colors in this plot. However, as we're moving deeper and deeper into the abutment, the concrete condition starts to improve. The middle plot represents sensor 3, which is approximately 6 inches from the concrete surface. And here, the compressive strength is improving. It's not great, but it's still considerably better than what we were seeing at the surface. And then at approximately 10 inches from sensor 4, we are seeing even more improvement in the bottom plot. This slide shows the compressive strength testing results for the cores. which were generally in line with IAPV testing results. And on the bottom are the test results for the rebar sample. Next, please. This is another bridge fire example. This fire was significantly smaller. It occurred near the pier cap that you see there. It damaged the pier cap as well as 2 precast concrete beams and the diaphragm. Next slide, please. So here we couldn't extract the cores from the beams because of the very congested reinforcement. So we used a slightly different approach. Here we combine surface measurements that you see in the color plot at the top of the slide with through measurements. Through measurements is a variation on the through tomography. So here we're not creating multiple paths between the sensors and the impact device. However, we're placing the impact device on one side of the element and we're placing the sensor on the opposite side. So in this configuration, instead of looking at the near surface concrete, we're looking through the entire thickness of the element. And this is illustrated on the schematic on the right side of the slide. Can you go back, please, Bill? Thank you. So if we compare the surface measurement plot that shows deterioration between 0 to 8 feet of the girder, the through measurements showed that deterioration or damage to the core of the girder was limited to 2 feet to 6 feet of its length. Next slide, please. And these are results for testing of the pier cap. So here we also compared surface measurements to through measurements and got very similar results. So through measurements showed that although there was surface damage from approximately 16 feet to 26 feet, the damage to the core of the pier cap was limited to essentially the top right corner of the pier cap. This is another example of fire damage. This was a car fire that occurred inside a parking structure. This car fire damaged the nearby column, the beam that you see in the photo, as well as the slab underside. We did impact echo pulse velocity testing on all of these elements, but I, in particular, wanted to show you the results for the beam. So the fire caused a visible delamination in the beam underside, and the owner wanted to have a contractor remove that for safety reasons. So we performed testing prior to concrete removal, and these are the images or the plots that you see on the left side of the slide. The top and bottom plots show the 2 vertical faces of the beam, and the middle one shows the underside. So here we collected measurements before concrete removal as well as after concrete removal. So this small area that you see on the right side of the middle plot is actually IAPV measurements that were collected on the freshly exposed concrete surface after the cover concrete was removed by a contractor. And as you can see, the measurements there are significantly better than the measurements collected from the surface, which indicates that as you move into the core of the beam, the core concrete is still in good condition. This is an example of a parking structure that was affected by flooding. This parking garage was built on a slight grade where one side of the garage was being periodically flooded. What you're seeing on the left side of the slide is one of the bays in the parking garage. And on the right side of the color plot for the corrosion potential survey, you're seeing some areas of active corrosion in areas that are periodically exposed to water, And on the right side of that plot, reinforcement is completely passive because it stays mostly dry. Can you go back, please? This slide also shows a corrosion potential survey plot for a column located on the side that's subjected to flooding. What we typically see in columns in flooded structures is that corrosion is limited to the bottom of the column, but the main question is how far does it extend? Next slide, please. And now I'm going to pass it over to Bill to talk about freeze-thaw and other flood assessments.
Very good. Thank you, Natalia. So for freeze-thaw, this was an example of a dam that had significant section loss in the concrete buttresses. On the right image, some of that section loss was in excess of 15 to 18 inches on both sides of it. And the question was, what's the condition of the core strength of the concrete buttress? So we needed to have access to both sides of that concrete buttress, which is about 8 feet wide. And we are very careful to lay out an accurate XYZ grid system. We need to know where we are on both sides of any element that we're doing through testing for. And the crossing wave paths, once we have all that information, we can take slices through the buttress, and the outside concrete was considerably weaker than the core concrete. And that was validated by horizontal concrete cores on this first and worst buttress that we did the evaluation on. They were bringing in some new equipment for the hydroelectric facility, and this was all part of a load rating analysis for the superstructure being supported on these concrete buttresses. Another example is a concrete pier that on the outside, the shotcrete repair had failed, the cover concrete was gone, and we were doing surface testing and through testing. The surface testing to the first 6 inches was not very good. The core strength of this pier was in excess of 5,500 PSI, and all 4 of these piers on this particular bridge was able to be salvaged. The final recommendation was to chip out the weak concrete and just do a perimeter surface overpour to preserve the structure. Another example case study is after a hurricane, there was some failure of sidewalk sections. These are supported on fill. On the left side of the left image, there's a sheet pile retaining wall with a pile cap on top. And the hurricane flood waters had come up so high and had washed out a lot of the soil, not only underneath the sidewalk sections that did fail, but there were some areas of the adjacent parking lane as well as the travel lane of the road adjacent to this wall. So the ground penetrating radar, the low frequency GPR, was able to determine, it looked through the concrete slab and documented where the voiding conditions were underneath the sidewalk and the roadway. Another post-flood assessment was for a spillway where, again, there was voids underneath the concrete slab, and the low frequency GPR would penetrate through the concrete and determine where those voids were. That's the image in the upper right. The 2 images on the bottom, the left side is a summary of the compressive strength from the pulse velocity information. That's the green and the orange and the reds, corresponding to the weak and strong concrete. And then the red and white plot was the delamination of the rebar within the concrete slab, and that information was from the impact echo data. Another post-flood spillway, a much larger one, was a couple of sections that were power washed in a phased approach, quantified the condition of the concrete as well as the voiding underneath it. Some parts of the spillway were founded on rock, some were on rubble, and some were on voiding. A dam riser and some outfall pipes were assessed, and there was no plans available on this riser structure, so we used ground penetrating on the inside of the riser. We bermed up to keep the water out just temporarily, and the GPR could confirm where the rebar spacing and depth of cover and horizontal and longitudinal bars were. Our Impact Echo pulse velocity equipment is waterproof, and we put it in the hands of divers to get concrete compression values of the concrete. So we put that all together, and that was used as a assessment, condition assessment for that particular structure. There was also an outfall pipe that we looked at that had some pre-stressing strands, and there was some delamination on those strands as well. That's the lower right image. A transit tunnel was flooded out, and the two duct banks in the middle image, shown right by that red arrow, all of the power line, utility lines were being removed. But the question was, what's the integrity of the concrete duct bank? Nobody wanted to have concrete rubble fall on the tracks. So over a 2-night period, we were able to assess about 4,000 lineal feet of both sides of the ducts. We had access at night, and we got information every 25 feet along there. We had a large crew in there working both sides with 2 sets of equipment. All of our equipment was on a little rail cart, and very effective. That the condition of that concrete duct bank, the abandoned one, both of them, was sufficient, and there was no concern for rubble or debris getting on the railroad tracks. And then after an earthquake, there was some visible cracking, and the concern was the extent of that. The repair strategy was to do a grout injection of these cracks, and as part of a QA/QC assessment, we were able to verify the condition of the concrete shaft prior to the grout injection and after the grout injection. On the left vertical image, the orange and reds and yellows show the weak areas adjoining to the cracks. And then in the post-crack injection, all the reds and oranges were eliminated. It was an effective and quantified QA/QC project for the grout injection. During a new placement of a concrete shaft, the spec was, this was about 11-foot diameter intake pipe, and the spec called it 12 o'clock high to make sure that there was a 10-inch thickness of concrete. The sides and the bottom, probably not a concern, but making sure the consolidation covered all the way to the top. And the spec said every 150 feet you had to drill a hole. It was about 3 miles of an intake structure, and that was an awful lot of holes. So an engineer and contractor approached us and said, hey, can't GPR effectively determine the thickness of concrete if it's in contact? And we said, absolutely. So the right upper image is the 900 megahertz that was mounted on a shaft, a spring-activated shaft, and the mule that was on the rail carts just drove down all 3 miles in about 2.5 days. We were able to complete that. Verified a couple areas that were slightly less than 10 inches. We did some validation testing, and the engineer, owner, and contractor were very pleased with the results of this. And just wrapping up, we have also installed our Impact Echo pulse velocity equipment on underwater ROVs. We have an exclusive relationship that we've collaborated for some time with ASI Marine. They do a lot of commercial diving. They've got some of the best ROV technology in the market, so they can do photogrammetry imaging, sonar imaging, and with our equipment, concrete condition assessment underwater. The large image on the left is the white bar that has mounted our 4-sensor array, and those black nubs are where the sensors are. The larger one on the right-hand side of that image is the electrostatic clicker image, energy impactor. There's some other pendulum apparatuses that we've developed for energy, and we also have the capability to do through testing a dam with the ROV on the water side of the dam, and maybe rope access or robots or something climbing on the dry side of the dam. So very proud of our ability and collaboration with ASI Marine. We've done a couple of, one case study here with that was a new intake structure that was constructed, and they wanted to see what the condition of the concrete was and the thickness of the new concrete. It turns out that the strength was right around the 5,000 PSI that was supposed to be. A couple of them were a little lower than that. We get this information by recording the compressional wave velocity, the shear wave velocity, Poisson's ratio, Young's modulus, bulk modulus, et cetera, to get to a compressive strength. Another one is where we verified the thickness of that outfall pipe and correlated that with the strength. So the y-axis on the left is the compressive strength, the y-axis on the right is the thickness of the pipe over the stationings for that particular one. So as a summary, just wanted to recap that, extreme weather are very common and they really subject structures to a lot of unplanned conditions, and deterioration can accelerate very rapidly, particularly salt water on rebar and corrosion and cracks. But the first step is to evaluate and to understand what the condition of these structures are. We've got a number of tools in our non-destructive testing tool belt: impact echo, pulse velocity, ground penetrating radar, corrosion potential testing, just a few of them. Sometimes cores are good, so destructive and non-destructive test methods are key to assessing the extent of deterioration beyond what we can see as engineers for observing conditions. Eric, do we have any questions here? That was all that Natalia and I wanted to share today.
Yes, we have quite a few, and nice job, Natalia and Bill. There's a lot of great information there, and hopefully a lot of people found quite a bit of that beneficial. So a bunch of questions coming up. So I'll just start off, and one of them was, what is the thickest through tomography is good for?
The thickest tomography that we've done, it was in a tremipore of a large bridge foundation, and it was underwater. It was about 28 feet thick. And again, we had to have accurate XYZ positioning systems with divers. We needed to know where we were on both sides of this large tremipore, but we went through the foundation that was about 28 feet thick.
Okay, thank you. Here's another one I thought was pretty interesting was, so say you're working on something like a vertical wall, but there might not be a specific surface or structure behind it, and you want to, are you able to get that wave reflection back, or do you have to do through testing on that? What if there's not anything behind the wall that you're trying to do that wave testing on?
Well, the impact echo will reflect off the back of the wall, and we would get a thickness. That energy just oscillates back and forth between the thickness of the wall. But if there's an anomaly within the wall, that thickness or amplitude or frequency would change. But to determine if there's anything behind the wall, I think it would be a combination. We would want to use the low frequency GPR to go through the wall. Hopefully there's not too much reinforcing in the wall that would inhibit the penetration. If there's a lot of steel and concrete, the electromagnetic signal needs to get through it and bounce back. So it might be a combination to determine the thickness of the wall and confirm that there's nothing behind the wall, or that there is a void behind the wall. Natalia, anything to add?
No, I think you answered it. I would just say that, there is a limit to the thickness that impact echo can determine, isn't there?
There is, yes. It is about 3 feet, and then for the pile lengths, the piles need to be a little bit longer than about 10 feet. There's a bit of a blind spot in there, but up to 3 feet, 3.5 feet, we can determine the thickness of concrete and where some delamination or voiding or anomalies might be within that concrete. Correct.
Okay. Thank you. Here's another one. And does impact echo pulse velocity testing sense the presence of rebar? If not, why do the pulses pass through the steel without change in velocity?
They do not detect the rebar, and it is the velocity or the frequency that goes through the aggregate, the concrete, and the reinforcement as a composite structure. It's all about the same thing. So if large aggregate or rebar doesn't separate any of those energy waves. They go through as a uniform based on the speed and the frequency that we're picking up these signals. That's a great question.
And here's another one, Bill and Natalia, I thought was pretty interesting. Bill, you touched on it at the end where you were talking about using some of the equipment with the ROVs and partnering with ASI Marine there. But what about, is there any options for remote performing these tests rather than having a person physically complete them? And I think the big question is, are drones or anything like that?
That is a very good question, and the answer is yes. First, there are robots that have various vacuum suction capabilities to walk up vertical surfaces and maintain connection with that, and we've done some research with those. As far as drones are concerned, I have seen, yes, that technology deployed on drones. It's usually in the front of it. And they kind of nose up to the structure, impact it, and collect the data. You have to have a steady hand with the drone operator, and it has to be configured that obviously the propellers are not going to be impacted. But that is out there. It is not something that NDT division or VCS has direct experience, but we're always trying to push ourselves on the innovation and research and development side of things. But it is out there.
Another one here. So have you experienced or heard of issues using GPR to locate rebar within electrical substations or around other sources of EMF? So there's a person here apparently runs into inaccurate results using handheld rebar finder. And yeah, I'll kick that to you, see what your thoughts are.
Yeah, that is a concern. If there's overhead power lines, we've experienced that at power generation facilities where there is a lot of current and voltage flowing through. That can impact the signal because it's electromagnetic energy, and it can definitely impact that. So where there is some stray current also around railroad tracks, there is stray current on that center line or overhead gantries, that can be an impact. It's not the GPR's fault. It's just the interference of the current when it's very, very close to the antenna.
Here's another one that I think comes up quite often is, we know that your impact echo pulse velocity testing does a really nice job with the depth of the crack. What about the width of the crack and the width of the crack throughout the crack and however deep it might be? How is it for identifying that?
The width usually is, visibly, we see that on the surface, and it doesn't necessarily quantify the width. For concrete cracking, I think could almost delegate things to surface cracking and structural cracking. And whether it's a thick crack or a thin crack, it is still a crack and has compromised the integrity of the concrete and ultimately the structure. So it doesn't tell us how wide it is, but we focus more on depth. Whether it's a 0 to 3-inch crack, a 3 to 6-inch crack, or something greater than 6 inches. These are all in depths. So no, it doesn't quantify the width, but if it's crack, it's a crack. Natalia,
Okay.
Anything to add there?
No.
Okay, thank you. And here's another one. So what testing would you recommend for a structure exposed to stray electrical currents and chlorides, but with cathodic protection? So I'm guessing that question is, it may have cathodic protection on it, but it may be exposed to either stray electrical currents and or chlorides. How would you guys attack that?
So we've done several projects on doing testing on like subway stations that have this exact issue, that are above ground stations. There you have to do a straight current evaluation, chloride testing also. But a regular corrosion potential survey, if you have influence of stray current, is not going to give you accurate results.
Okay. No, that's helpful. Thank you. And I know we're getting right at around 3 o'clock here, well, Eastern time for me. But there was just one or two more questions and then we'll wrap up. So how does reduced weight concrete or lightweight aggregates affect sonic wave propagation / velocity?
That's a very good question. We do use the density of concrete in our calculation, and that's usually somewhere around 145 pounds per cubic foot. But when we're dealing with lightweight aggregate or lightweight concrete, we would look to quantify that and adjust our calculations. So it directly affects our results for the compressive strength from the velocities. Great question.
So also when we collect the cores per ASTM C42 together with the compressive strength, we get a density for the concrete. Correct. Which can be used directly in the calculation. So especially if there is uncertainty whether the concrete is normal weight concrete or lightweight concrete, collection of at least some cores can be very helpful.
Right, and I think we'll wrap up with this one. I thought this one was pretty interesting. So for the fire damage assessment, utilizing the testing equipment described makes sense for major structures that have been covered in the presentation. For minor concrete elements, however, so for example, residual foundations, maybe it's a pedestrian bridge, small diameter concrete piers, do you recommend any evaluation methods that don't require heavy analysis equipment, such as visual assessment, the color, the concrete, hammer testing, those types of things, outside of maybe what you would see here? Or is it applicable for some of those smaller bridge elements?
So I think you have to look at risk, not necessarily the size of what you're testing. Yes, you can look at the color of the concrete and try to relate that to the temperature that the concrete was exposed to. But that doesn't work for all types of concrete aggregate. So if you have a silicate aggregate or a limestone aggregate, your concrete will turn a pinkish color if it was exposed to temperatures above 300 to 400 degrees Celsius. And at that temperature, we would, like 400 degrees, we would expect the steel mechanical properties to start to deteriorate as well. So if your structure poses a risk, if it fails, I think evaluation is still warranted. Limited information can be gained from visual inspection. And relying on color change alone, especially without knowing the aggregate type, may not be sufficient. Hammer testing is very good. It's going to identify areas of delaminations. However, that's not going to indicate whether the concrete deterioration extends beyond the concrete surface. And I think that's the major concern. Is the concrete damage limited to the surface, and is the rest of my elements still okay? Other surface testing methods like Schmidt hammer, again, are limited to the surface. So they're good for identifying the limits of the area that was affected by the fire, but they wouldn't provide information for concrete condition beyond the surface.
The only thing I'd add, Eric, would be that, Windsor probe, Schmidt hammers, hammer sounding, my ear is only as good as I can hear it. It's a qualitative assessment. If you want to know the condition of the concrete, you would want to do a quantitative assessment, and that's where the pulse velocity and impact echo really helps quantify the condition versus qualify. But some great questions here this afternoon. Thank you to everybody.
Yeah, and I think on that one we'll start to wrap up. But Natalia and Bill, thank you for that, and really well said there, and including the it's about identifying the risk and how to move forward and getting that. So thank you both. So we're going to wrap up here. If we did not get to your question that was posted, no worries on that. We will be sending them over to Bill and Natalia, and they will respond back to you. So appreciate everyone for sending those in and participating. And if you found today's session valuable and want to keep the momentum going, the CPA has another webinar coming up on September 11th. The next session is going to focus on investigating hidden structural conditions. And you can register by scanning the QR code on the screen, or you can head over to our WeSaveStructures.com/webinars to sign up for that. And again, if you have any follow-up questions for Bill or Natalia, feel free to reach out to either of them directly at the contact info provided here. And just a reminder, everything, including the PDH credit link, will be shared with you by tomorrow at 4 p.m. Central Time. And that wraps it up. So again, a big thank you to our presenters, Natalia and Bill, and a big appreciation for everyone who took the time out of their busy schedule to join us today. So hopefully we see you at a future webinar on September 11th, and we can all get out there and save some structures. Thank you.